Welcome back, guys, and in this tutorial on complex numbers what we're going to be looking at is the conjugate root theorem. Now the conjugate root theorem is very similar to the factor theorem we studied in algebra, but obviously it's specifically about complex roots, about imaginary roots. Okay, so our rule for the conjugate root theorem is if z is a root of an az to the power of n plus bz to the power of n minus 1 plus dz plus c equals 0, which is basically just an expression in complex numbers in z, where a, b, c and d are elements of or, then the conjugate of z with a little hat on it, remember, is the conjugate of z, is also a root. Now you remember from our video on dividing complex numbers that the conjugate of a complex number is when we take the imaginary number and we change the sign of the imaginary part. Another important thing we need to remember from algebra when we looked at the factor theorem is this little equation here, which is not in the log tables, it's one we need to remember. That x squared minus the sum of the roots times x plus the product of the roots equals 0 is how we can form a quadratic equation. Now we're going to use this rule in example 1 here, where it says if z is equal to 1 plus 5i is a root of the equation a z squared plus b by z plus c equals 0, where a, b, c are elements of or, find a possible set of values for an element for a, b and c. Well, we know from the conjugate root theorem that if z plus 5i is a root, then the conjugate, which is 1 minus 5i, is also a root. So we have two roots of our complex quadratic. So we now have a by z squared plus b by z plus c is equal to 0. But what we know here is that if we take this and change our x to a z, we should be able to find our quadratic equation with our two roots. So what we're going to say here then is z squared minus the sum of the roots. Now remember, the word sum means to add the two together. So minus 1 plus 5i plus 1 minus 5i by z plus the product of the roots. Now remember, product means multiply. So 1 plus 5i times 1 minus 5i equals 0. So we get z squared minus, and I can see my two complex numbers inside the brackets cancel because one's a plus and one's a minus. So we get minus 2z, because 1 plus 1 is 2, times by a minus makes minus 2z. Here we need to multiply out the brackets, which means I'm really going to have plus 1 by 1 minus 5i plus 5i by 1 minus 5i is equal to 0. And now I'm going to multiply them out. So I have z squared minus 2z plus 1 minus 5i plus 5i minus 25i squared. And this is the important part we need to remember, is that we know that I squared is always equal to minus 1, and we need to substitute that in. Now I see my minus 5i and plus 5i cancel. So I now have z squared minus 2z plus 1 minus 25, and instead of I squared I'm going to sub in minus 1. A minus by a minus makes a plus, so he's now plus 25, which means my final answer is z squared minus 2z plus 26 is equal to 0. Which means a is the number hidden in front of z squared, which we know is 1, b we know is minus 2, and c, the constant, is 26. So I'm going to finish up over here with therefore a is equal to 1, b is equal to minus 2, and c is equal to 26. And that's how we do example 1 using the conjugate root theorem. We're now going to look at example 2, guys. In example 2, it says, given that z is equal to 2 plus I is a root of z squared minus 4z plus 5 equals 0, show that the conjugate of z is also a root. Well, I know that if z is equal to 2 plus I, that means the conjugate of z has to be equal to 2 minus I. If it's a root, when I sub it in for z, it should multiply out to give me 0. So I'm going to take my quadratic, which is z squared minus 4z plus 5 equals 0, and instead of z, I'm going to sub in 2 minus I to show that it's a root. So I have 2 minus I squared minus 4 by 2 minus I plus 5 is equal to 0. And now I'm going to start multiplying. So what I see here is I need to split my brackets. So I have 2 by 2 minus I by 2 minus I. Minus 4 by 2 is minus 8, plus 4i, plus 5 is equal to 0. So now we're going to multiply again. So 4 minus 2y plus I squared minus 8 plus 4i plus 5 is equal to 0. So now we need to start simplifying. I can see 4 minus 8 is minus 4, plus 5 is 1, minus 2i is minus 4i, plus I squared we know is really minus 1, plus 4i is equal to 0. So I can see my 4i's cancel anyway, and I have 1 plus minus 1, which also cancels, so I get 0 is equal to 0. So I can now say, therefore, the conjugate of z, which is 2 minus I, is also a root. And remember to always finish a question like that with a conclusion, guys, because it does say show at the start of the question. Okay? So that's now example 2 on the conjugate root theorem. The next one we're going to look at is finding the third root if we have a cubic complex number. Okay? So it says, given that z is equal to 1 plus 2i is a root of z cubed minus z squared plus 3z plus 5 is equal to 0, find the other two roots. Well, using the conjugate root theorem, we know that if z is equal to 1 plus 2i, then the conjugate, which is 1 minus 2i, is also a root. And we can use these to find a quadratic, using our formula that z squared minus the sum of the roots by z plus the product of the roots is equal to 0. So we're going to have z squared minus 1 plus 2i plus 1 minus 2i by z plus 1 plus 2i by 1 minus 2i is equal to 0. Which means inside my brackets here, my 2i's cancel, so I'm left with minus 2z. Here I need to split the brackets to multiply. So I have 1 by 1 minus 2i plus 2i by 1 minus 2i is equal to 0. So we have z squared minus 2z plus 1 minus 2i plus 2i minus 4i squared is equal to 0. So again, my 2i's both cancel. We know that I squared is really minus 1, which I need to sub in for. So we have plus 1 minus 4 by minus 1 is equal to 0. Minus 4 by minus 1 we know is plus 4. So I get z squared minus 2z plus 5 is equal to 0. Now I can use my quadratic here to divide into my cubic to find the third root. So I'm going to take my quadratic and I'm going to move it over here to set up my long division, just like in the factor theorem. Okay? So my quadratic I know is z squared minus 2z plus 5, and I'm going to divide it into the cubic given to me in the question, which is z cubed minus z squared plus 3z plus 5. So the first thing I do here, a bit of a reminder for long division in algebra, I'm going to multiply z by z squared to get z cubed. Then I'm going to multiply it by the other two terms here as well. So I get minus 2z squared plus 5z. I'm going to underline and change all the signs, which means the first ones cancel. I get 2z squared minus z squared gives me z squared, minus 5z plus 3z gives me minus 2z, and I bring down my plus 5. So now I can see to get z, all I need to do is multiply by plus 1, which will give me z squared minus 2z plus 5. When I underline and change all my signs, all three cancel, which shows me that I have completed the long division correctly, and I have my last root. That z plus 1 is equal to 0, which means my last root is really minus 1. So I would finish my question with, therefore, z equals minus 1, z equals 1 plus 2i, and z equals 1 minus 2i are the three roots of the cubic. So as you can see, guys, the method for this is very similar to the method we went over in the factor theorem, but we just need to know about the conjugate root theorem to give us this little trick at the start. Okay? Now there was a lot to take in that tutorial, so take your time, play the video again, go back over it, and then we'll try a few questions. Thanks, guys.